in this session we will be discussing about molar conductivity, that is molar conductance. Molar conductance. In your previous session you can observe we have studied about equivalent conductance. So in this session we will be discussing about this molar conductance. It is represented by lambda m. Lambda m. Remember, equivalent conductance is represented by lambda eq. This is your lambda m, that is molar conductance. Now what is the definition of molar conductance? It's same as your equivalent conductance. It is the total conductivity offered by a solution of the electrolyte having 1 mole of an electrolytic substance. So in equivalent conductance it is equal to 1 gram equivalent weight of a substance. In molar conductance it is equal to 1 mole of a substance, electrolytic substance in the aqueous solution. So I can define it as, it is the conductance offered by all the ions present in 1 mole of a electrolytic substance when dissolved. So very important, here it is 1 mole. There it is 1 gram equivalent weight, here it is 1 mole. So it is the total conductance offered by all the ions that is present in 1 mole of an electrolytic substance when dissolved. So this total conductance offered by a solution with 1 mole of the substance, electrolytic substance, is called as your molar conductivity. As your equivalent conductance, your molar conductance is also dependent upon the volume and concentration of the electrolyte. That is, your lambda m is equal to kappa, that is specific conductance or conductivity, what do you call it as conductivity, into V. So molar conductance is equal to kappa specific conductance into volume. Here volume is, it's the volume of the electrolytic solution having 1 mole of the substance. Here it is the volume of the solution, having 1 mole of the electrolytic substance. Which means that it's a solution with the number of, that is the solution with substance in mole terms, which means this is a molar solution, that is molarity. It is a molar solution, which means it is related because number of moles dissolved in liters of solution is nothing but molarity. So this is a molar solution, hence it is related to molarity. So what is molarity? We know molarity is equal to number of moles of substance divided by volume in liters. We know this. Molarity is number of moles of substance divided by volume in liters. So if I substitute for volume here, it becomes volume V in liters is equal to number of moles divided by molarity. Number of moles divided by molarity. We know that number of moles is 1 mole. It is equal to 1 mole. So this becomes V in liters is equal to 1 divided by molarity. 1 divided by molarity. So in liters, if I want to convert into ml, that is cm cube, V in cm cube, or simply it's in ml, means it is equal to 1000 divided by molarity, that is 1 into 1000 divided by molarity. So substituting here, the equation becomes lambda m is equal to kappa, your specific conductance, into 1000 divided by molarity. So, which means that here the molarity, that is molar conductance, it is equal to kappa, the specific conductance, into 1000 divided by molarity. Molarity is the concentration of the solution. So, this is about the molar conductance. So, as we know, now we have deduced your lambda m is equal to kappa into 1000 divided by molarity. Even lambda EQ can also have such an equation, that is your equivalent conductance, that is equal to kappa into V, where V in your previous session I have told you it is the volume of solution or electrolytic solution with 1 gram equivalent weight of the substance. So 1 gram equivalent weight in a solution means it is nothing but normality. So 1 mole of a substance, it's related to molarity. So in the same way, 1 gram equivalent weight of a substance is related to normality. So what is normality? It is equal to number of gram equivalent weight of a substance divided by volume in liters. That's your normality. So again, if I equate this equation for volume, what it becomes? It becomes volume in liters is equal to, so number of gram equivalent weight is 1 gram equivalent weight. You can observe here it is 1 gram equivalent weight. So this becomes 1 divided by, number of gram equivalent weight is 1. So 1 divided by normality. So if it is in ml, V in ml, this becomes equal to 1000 divided by normality. So upon substitution, it becomes lambda EQ is equal to kappa into 1000 divided by normality. So this is an equation for your equivalent conductance, and this is the equation for your molar conductance, which will be utilized to do some numericals based upon these molar conductivity as well as molar conductance as well as your equivalent conductance. So now we have discussed about 3 types of conductance. The first one is specific conductance, or just simply call it as conductivity. Then equivalent conductance, then molar conductance. So 3 types of conductance we have studied. One is your kappa, that is your specific conductance, simply calling it as conductivity. It is the conductivity offered by all the ions present in 1 cm cube of your electrolytic solution. Then lambda EQ, equivalent conductance. It is the conductance offered by all the ions present in an electrolytic solution made by 1 gram equivalent weight of the substance dissolved in it. Then lambda m, that is molar conductivity. It is the conductance offered by all the ions that is present in an electrolytic solution whose concentration is, whose solution is prepared by dissolving 1 mole of a substance. So the keywords are, it's your 1 cm cube of solution, this is your 1 gram equivalent weight, and this is your 1 mole. So these are the keywords to remember what is conductivity or specific conductance, what is equivalent conductance, and what is molar conductance. Specific conductance, that is the conductance offered by 1 cm cube of a solution. It is the conductance offered by a substance with a mass of or a concentration of 1 gram equivalent weight of the substance. Lambda m, it is the conductance offered by 1 mole of a substance when dissolved in the aqueous solution. So these are the 3 types of conductance we have studied till now. So the next thing we have to study is how to determine your specific conductance, that is your conductivity, with a experimental method. So let us see the experimental method of determination of the kappa, that is your specific conductance, through Wheatstone bridge. As in your previous session I have told you, determining the conductivity or resistance of an electrolytic conductor is not so easy as your solid conductors. We have studied about two types of conductors. The first one is solid conductors, electronic conductors. The other one is electrolytic conductors, that is nothing but your aqueous conductors. So as a result, just by taking a solid conductor, how easily you can do a conductance or resistance measurement, it cannot be done in such a way with your electrolytic conductor. So as a result, for an electrolytic conductor, we have also discussed in the previous session, we require a cell called as conductivity cell. So for determining this kappa, that is your conductivity also for an electrolytic solution, you require a special apparatus which is called as conductivity cell. So this is your conductivity cell. Conductivity cell, it has your electrolyte whose conductivity has to be determined. This is your electrolyte whose conductivity has to be determined. There are two electrodes dipped in. Positive and a negative electrode. The distance between these two electrodes is your L, that is distance between the two electrodes, and this area of cross section of the electrode is your A. Area of cross section is your A. So L by A is your cell constant. So this is your cell. This is your conductivity cell. So this cell is closed, sealed up in order to find the conductivity of this electrolyte. Its electrolyte is unknown. So this is your unknown. You don't know the conductance of this electrolyte. You are determining the conductance of this electrolyte. So conducting the experiments with respect to calculate the conductance of this electrolyte cannot be done in a straight way. That is, you have to first find out its resistance, followed by 1 over inverse of your resistance is nothing but your conductance. So directly we are not determining the conductance of this electrolyte. Instead, we are doing a experiment wherein you know the resistance of this electrolyte. From the resistance, you are calculating the conductance of this electrolyte. So that experiment which determines the resistance of this electrolyte is your Wheatstone bridge. Wheatstone bridge. So you have an experimental thing with your Wheatstone bridge even in your physics. So let us see what is this Wheatstone bridge. So Wheatstone bridge is a circuit of 4 resistors wherein 3 resistance is known and 1 is unknown, and whose unknown resistance is determined by varying these 3 resistors which we have been used. So the bridge looks like this. So this is R1. Resistor 1, this is R2, resistor 2, say this is R3, this is R4. Here you have to connect it to a galvanometer, and this is connected to a current supply. Very importantly, the current supply should be an AC current. I'll tell you why it should be an AC current. Here it is your galvanometer. This is your galvanometer. Here R1, R2 and R4 are your resistors wherein you can vary the resistance. So variable resistors, R1, R2 and R4 are variable resistors. R3 is your unknown. Unknown is nothing but your conductivity cell. So this conductivity cell should be connected here. So I'll just put a here. So this is your conductivity cell. So this is your cell here. You have to connect this conductivity cell to your Wheatstone bridge at R3. So R1, R2, R3 are variable. You can put resistors, remove resistors. You can vary the resistors. But R3 is unknown. So using these 3 resistors variance, you can calculate this R3. Now R1, R2 and R4 are variable, R3 is unknown. So it is connected to an AC current. I'll tell you why AC current is. So AC current is because if a DC current is used, that is a direct current is used, the ions present in this electrolyte, instead of conducting, they move towards the respective electrodes and get deposited. As a result, you use an AC current. AC current is alternative current, wherein the electrodes keep on alternating. That is, a cathode becomes an anode, anode becomes a cathode, wherein there is no deposition of ions. But if you use a DC current, a direct current, what happens is, instead of conductivity, the ions will move towards the respective electrode and they get deposited. Deposition of ions makes this electrolyte become a non-conductor of bad conductor of electricity, that is, electricity cannot no more pass through this cell. As a result, instead of DC current, you have to use a AC current. So this is your Wheatstone bridge. It's ready with your conductivity cell connected. You are varying R1, R2 and R3. You are taking out the resistors, putting the resistor such that the Wheatstone bridge galvanometer shows 0 reading. So you have to balance the Wheatstone bridge. You call it as balancing the Wheatstone bridge, wherein you have to remove R1, R2 and R4 such that the galvanometer shows you 0. That point of your experiment is called as balanced Wheatstone bridge. It is called as balanced Wheatstone bridge. So R1, R2 and R4 are variable resistors. I think you have seen the resistors in your physics lab. So you can add the resistance, you can remove the resistance. So you can do anything with your R1, R2 and R4. While R3 is your conductivity cell, this is your R3, it is unknown. So now your variable resistors you are varying such that your galvanometer shows you 0 reading. It has to show a reading of 0. So such instance of experiment wherein the galvanometer shows you 0 by varying these resistors is called as a balanced Wheatstone bridge. Now by using the formula Ohm's law, you can calculate your R3 from R1, R2 and R4. So when the galvanometer shows you 0, it means the balanced Wheatstone bridge is balanced. Now applying the formula, R1 by R2 is equal to R3 by R4. You can calculate R3 since R1, R2 and R4 are known. You are varying the resistance. So as a result, you know R1, R2 and R4. As a result, you can calculate it as R3 is equal to R1 by R2 into R4. So what's your R3? It's your unknown. So you get the resistance of your electrolyte that is present in your conductivity cell. That's your R3. So R3 is your resistance. So by balancing the Wheatstone bridge, by applying this formula, you have calculated the R3. That is, it's the resistance of your electrolytic solution taken in the conductivity cell. We know the equation. We have already studied in the previous sessions, wherein kappa is equal to G into G star. G into G star. That is, specific conductance is equal to G conductance into cell constant. We know that conductance is 1 over resistance. 1 over resistance into the cell constant is L by A. L by A. We know resistance. From the experimental data we have recovered what is resistance of the conductivity cell. So apply here. L by A, we know the length, that is the distance between the two electrodes. It is fixed in your conductivity cell. A, area of cross section of an electrode, which is also fixed. So we have all these data, wherein after applying all these data we get your specific conductance. So like this, you can calculate your specific conductance of an electrolytic solution using a conductivity cell and a Wheatstone bridge through this formula. So RS, this R3 conductor resistance that has been calculated, L distance between the two electrodes in the conductivity cell, A is the area of cross section. So substituting this, you get your specific conductance, which has been experimentally determined by your Wheatstone bridge experiment. The unit of molar conductivity, unit of molar conductance, that is lambda m, is ohm per ohm, meter square or centimeter square per mole. This is the unit of lambda m. So lambda eq you know already, lambda eq is per ohm, meter square per gram equivalent. So this is of your lambda m, while this is of your lambda eq. And you know about your kappa, that is specific conductance, it is per ohm per meter.